you, David.
Hi, everybody. I'm very glad to be here. As Ben just alluded to, I'm the Knight Junior Chair of Data Science, and I'm Associate Professor with the Computer Science Department and a core IDSC faculty member. My PhD student, Parnia Favardine, is also in the audience, so she's been a part of this work as well, so a special thank you to her. And I'd like to talk today about semi-supervised image classification. And before we get into that, I'd like to just have a couple of representative images of a problem that today is not very difficult by modern standards, but was incredibly difficult for a very long period of time, and that is, what is the difference between a cat and a dog? Right, they're both the same color, they're the same texture, they both have 2 eyes, 2 ears, and a nose. They're both sitting on similar colored bed sheets. So to a computer, they used to look exactly the same. Now they look very different. But the reason why they look different is because of the creation of a very well-known data set. I know this is old news for many of you, but a very well-known data set, ImageNet, which has tens of millions of annotated images. So people meticulously compiled this data set together, and it was, I think, in 2015 when there was a neural network architecture with 64 million parameters that could ultimately classify the ImageNet data more accurately than a human. So, just with that amount of context about how hard this problem really is, and, not to talk too much about the machine learning, but, this didn't just happen. We needed to have people go through 14 million images and put them into categories. I think that's the part that people don't really talk about very much, is all of the human annotation. The people that are working on those kind of tasks, a lot of them aren't really paid a great wage. But you look at other application areas and it can be a very different story. For example, with medical imaging, the problem is that very few people have the medical training necessary to even tell what the medical conditions are, to be able to analyze the images. And even when they do, they may disagree. Right? So we end up with this problem where the human annotation is really powering a lot of the AI. But it's not an easy thing to solve. And I just want to look at, this is just a really simple problem. Here's 2 semicircles, and let's separate them. And on the left, we have a supervised machine learning problem where somebody meticulously went through and said, oh, this dot goes to here, this one goes to here, and you can see how easy it is for a machine to be able to find the difference between them. But if we only have a very, very small amount of annotation, right, then the machine has to figure it out. And you can see here we only have 4 points that are labeled, and the light ones, that's what it should be, but let's say nobody ever annotated which one is which, right? They'd all be the same. We might not be able to separate the 2 classes very easily. And that's really the problem with semi-supervised learning. How can we reduce this annotation burden and make models that can work with a lot data, but not data in more of its natural form. So, one of the things that we have to think about with semi-supervised learning is that the kinds of methods that have a potential to work for this problem are based on certain kinds of assumptions. There is something called the smoothness assumption, which is that if 2 samples are similar, then they might have a similar label, or if they're close together in the image space and they're close together in the label space, right? There are, or perhaps close together in some augmentation space. So this is actually something that's nowadays, with some of the recent progress in semi-supervised learning, I would say has really taken over in terms of the assumption that people are most commonly relying on. It leads to a method called contrastive learning that we'll talk a little bit about. But another one is the manifold assumption, which is that you can do some low-dimensional extraction of your space. You can take a high-dimensional space and project it to a low-dimensional. And of course, the problem is that if your dimensions don't represent the things that actually make your data different, If you're just representing the things that make your data look different, such as is it dark or light out? Is it indoor or outdoor? That might not be what you're looking for, even if it changes the pixel color by a lot, right? So, things like that. Dimensional reduction could be lossy, which could be a problem. Another common assumption people use is clustering. So perhaps we can find some clusters where if we find a point that's representative, maybe the nearby points, we could put that into a cluster. And then from there, we can try to come up with pseudo labels of what the data could be or some pseudo representation. And of course, the problem with that is something called confirmation bias, right? So if the model makes some mistake and puts the point in the wrong cluster, it could use that mistake and reinforce its prior error and start diverging. Imagine if somebody who believes in the flat Earth had access to the internet, right? They're going to find more and more information to confirm their earlier hypothesis, right? And a machine learning algorithm that makes a small mistake in the beginning could reinforce that error in kind of a similar way. Before we move on, I also want to talk about something called image augmentation. And this it tends to just be kind of Photoshop operations, rotation, changes in contrast, blurring, shearing, histogram equalization, things like that. This is something that for most data sets does not really affect, you could flip an image of a parrot or zoom in, and it's still a parrot. And this, yes, it is specific to images, but you'd be hard pressed to find a set of images where changing the intensity a little bit or where shifting the image a little bit does not change the meaning of the image very much, right? So yes, it is kind of a domain knowledge, I guess, but it's something that's very generic that crosses many domains, that this could be something that's quite valuable. And in fact, there's a branch of learning algorithms called contrastive learning, which is, well, if we make some change if we augment the image, then we want those augmented images to appear similar to the machine. So that way we don't need to know what the image is of. All we need to know is that if we change it, we're not changing it by much. We're not changing the meaning. And so that's really kind of the branch, and that's of course based on the smoothness assumption. That's the branch of approaches that seems to be performing the best right now, but people have looked at approaches that are based on all of the various methods. So with that in mind, one thing that we were looking at is, these are the assumptions people are making, these are the techniques, but then are there any problems? Because the idea that we're going to take images and try to predict what their label might be is actually, that's actually making use of the cluster assumption, and that approach is ultimately related to a classical statistical framework called expectation maximization. So we looked really closely at that, and we found a problem with the way people are going about it right now. And that problem is that it's not really able to handle outliers very well. And by outliers, I mean, well, like I was talking about before, what if we label the sample incorrectly to begin with? Well, then we're going to reinforce that error. So how can we actually identify samples that are outside of the knowledge of the ability of the machine to understand at its present time, so that we are not actually doing that quite as much, that we're able to be a little bit more conservative? So that's something that we've taken a much closer look at, and we've integrated that into a hybrid model that we have a nice long name for, and then we call it SCOPE for short. But this technique, it combines aspects of the contrastive learning with augmentation of various degrees of difficulty, along with this outlier removal to make sure that we're not labeling that if we make a bad label, that we're at least aware of which samples are outside of the understanding of the current level of prediction, so that we don't reinforce those errors in subsequent iterations. So, we're going to have a poster where if we can go over this chart in more detail, but just to kind of express that this is really trying to make use of that outlier removal to prevent it from spiraling off onto the wrong track. And we tested this on a set of small image data sets, Cypher 10 and Cypher 100. We found that it actually greatly improved performance. It's currently achieving 93.5% accuracy on an image classification task with only 4 labeled images per category. So we've gotten it down to just 4 labeled images. So 50,000 images, but only 4 of them are annotated, and all of the other ones are not annotated. So that's a notable improvement over some of the other techniques that have been developed up to that point. And also, we had applied this to a larger data set with 100 categories, and we found that it also made a notable improvement, although it wasn't to the same magnitude, because it's a more difficult problem. So that's something that we've been looking at, and then along those lines, we've been looking at this image augmentation as something that seems to be adding a lot of information. Because actually, when we look at the methods that didn't use image augmentation, it's not even in the same ballpark. The ones that are not augmenting the image aren't even more than 45% accurate. And these are really sophisticated methods that are making use of cluster and manifold assumptions. So in that case, maybe we need image augmentation to really take the front seat a little bit. And so we've actually started an open source project that we call TorchRand Augment to integrate image augmentation into the layers of a neural network directly, so that this isn't a pre-processing, that this is something that the network can actually do through PyTorch. And we did this by actually making use of PyTorch as a parallel assembly language, so we can implement some general purpose algorithms, and just showing that we did see a notable improvement in the performance of the image augmentation, but it's not really about performance. What it's about is that I really think that if image augmentation is adding that much information to the space, that making it so much easier for the model to understand these kinds of complex data sets, that perhaps we need to find a way to integrate it more tightly into the neural network architecture. So that's kind of an ongoing and future extension of the work that I've been showing here. But I just wanted to talk a little bit about what we're doing to try to reduce the need for labeled data, because I think that that's something that's an important problem that can cut across many disciplines. And I thank you all for the opportunity to talk to you about this research. Thank you.
Thank you, David. Any questions for David?
Yeah, so it's great stuff, and it's clear that say the data augmentation in particular works well with images, because you can have a human validate that a given transformation doesn't, like, this is still a parrot, But are you aware of, or is there active work in doing this in more structured data cases, like, say, whether a customer will churn, whether the propensity to buy based on all these features, where a human looking at the transformation can't say a priori if that's still the same person in terms of those predictions you'd want to make?
Yeah, absolutely. Yes, there are. And, along those lines, the idea of the machine learning the transformation, that's really in the realm of generative AI, generative methods. So, we've looked at that, generative adversarial networks. It's still with images, but to generate images without human oversight as to how it's doing it. And that can work very well. But you need to have a lot of data, and sometimes you need to have more data than you would think, in the sense that the more data you have, the easier it is for the machine to learn a general function about your space. And if you have less data, then domain knowledge or injecting some kind of knowledge about your problem can really help a lot. In fact, it can help quite a bit. We had a problem where we were looking at generating X-ray images for COVID-19 pneumonia. And we spoke with a radiologist who said, you know what? You should be segmenting the image because it's trying to generate bones. What does bone have to do with pneumonia? Why is it doing that? And we did the segmentation, and of course, it's something that they could tell us and we could understand it, but it really came from them. They're like, they looked at our images and told us that, and we did that, and we got our sample size down to 10 images. That's all we needed, instead of 10,000, which was the next closest paper, right? So, I think it's one of those things that if you're trying to work with a smaller sample, having some way or some function that can represent some insight could be very helpful and can really replace the need for a large amount of data.
Okay, we have time for one more quick question.
Oh, thank you. Very informative presentation. I like it. The idea is very interesting. My question is, based on my experience, when you do multiple classes classification, when you increase the number of classes, the accuracy decrease. So in that results slides, did you show the number of classes? So
Yes.
When you increase the classes, the number of classes, the accuracy increase.
No, it did not. And in fact, we saw the same thing, that when we increase the number of classes, this is the number of labels. So when we increase the number of labels, the accuracy increased. But when we switched from 10 to 100 classes, the accuracy really fell down to 57, which was still better than some other methods, but it's still much more difficult with more classes, and we saw that in our results as well.
Okay, thank you.
Thank you, David. For our last